Hey everyone, and welcome to today's lecture, recorded remotely. Hopefully, you're all viewing comfortably at home. Take advantage of this opportunity. Maybe grab some snacks or things to keep you awake and focused as we go through the topic of today's lecture, which is going to be focused on boundary value problems with a focus on mechanics. So, boundary value problems will give a definition of exactly what that means and why we care about boundary value problems. But before we dive into that, let's do a little bit of a review from what we covered in the previous lecture, which was presenting this comprehensive summary of all the governing equations in mechanics, and more specifically on the three-dimensional theory of solid mechanics and linear elasticity theory. So, this is the subject that I covered in a previous course, actually, and all of these subjects actually all tie together quite nicely. But to provide you with the summary of what we ended on last lecture, we came up with these governing equations of mechanics unified under these three different unifying principles. Compatibility, which in effect gave us a relationship between some description of motion in the form of displacement and the resulting relative deformation that occurs in some contiguous solid piece of material measured in the form of strain. And compatibility gave us this relationship between the resulting displacement field, a description of how individual material points might move or deform, and that deformation could potentially vary as a function of spatial position. Hence, we describe displacement not just as the displacement as individual points, but as an entire displacement field that varies with position. And if we took the gradient or the spatial derivative of the displacement field, then we get some measure of relative deformation. And from that, we can derive this description of strain in a three-dimensional context. So compatibility and these strain displacement relationships gave us this description of a strain tensor, this 3x3 array of strain components, which was related to in fact, the gradient of the displacement field, itself a tensor. And more specifically, the strain tensor was the symmetric part of the displacement gradient. The next set of equations that we derived was this concept of a constitutive law that linked our description of strain, this strain tensor object, to the resulting stress tensor object that we had come up with previously. And this set of equations relied upon an assumption of linear elastic material behavior, which is arguably the simplest possible relationship between stress and strain that you can come up with, sometimes also called Hooke's law. And we also supposed that that relationship exhibited isotropic behavior. So the material behavior didn't really exhibit any difference in apparent stretching behavior, regardless of what orientation we decided to stretch this chunk of material in. It would seem to exhibit the same kind of relative stiffness in any kind of direction that we might choose to pull it in. And that resulting stress-strain relationship, or that constitutive law, involved this relationship between the strain tensor, a rank 2 tensor, and the resulting stress tensor, also a rank 2 tensor, which required the definition of this rank 4 elasticity tensor, which made things quite a bit more complicated, but at the same time we could also reduce that down under these assumptions of linear elastic isotropic material behavior to come up with slightly simpler expressions expressible in terms of only two unique elastic constants. And then finally we came up with these equations governing equilibrium, which basically provided a statement of force equilibrium in a point-wise sense throughout the entire body that we were looking at. And these equilibrium equations, we provided several alternative ways of how we derived them, led to these statements or governing differential equations expressed in terms of this stress divergence term plus whatever extra body forces had to all sum up to be equal to the zero vector, and that had to be true, again, at every single point in the domain. In addition to that, sort of as an aside, Also, an important consequence of the fact that if we were to consider imposing moment equilibrium on any small chunk of material in this particular body or domain of interest, then in order for us to maintain that condition of moment equilibrium, we also had to have this local criterion on the stress tensor being symmetric. So not only do we have this governing differential equation basically telling us the sum of forces equals zero at every small kind of chunk of material in this domain, but also the stress tensor has to be symmetric. If you like, that's a description of sum of moments equals zero. All right, so we had all these equations, a total of 15 different equations, but really, I hesitate to call them just 15 equations. I like to think of it as 15 equations that have to be satisfied at every point in the body, and that has to be true, for possibly an infinite number of points that might lie in some continuum body of interest. So we put all these equations together, and in fact, if we wanted to, we could consolidate them further. We could take displacement, which we insisted, owing to the requirements of compatibility, that the displacement field had to be a continuous function of position. That was a requirement that if the body underwent some deformation process, then in order for that deformation process to be regarded as a compatible deformation, we required that the resulting deformation didn't result in the body splitting apart at any location. And that statement is effectively equivalent to insisting that the displacement field, this continuous function of position describing the displacement of individual material points, that the function that describes the displacement and how it varies in space has to be a continuous function. And so we restrict our attention now to functions that are in fact continuous functions defined over whatever particular domain we're looking at, and hence we'll use our conventional notation to refer to the displacement field as such, as belonging to the set of all possible continuous functions. From that, we could take that continuous function and plug it into our relationship for our strain displacement relation. We could plug that into the equation that we had for the stress tensor, depending on the strain, which in turn depends on displacement. And we could combine that again further with this force equilibrium equation to finally come up with one governing equation to rule them all, if you like, giving us just a final governing equation expressed solely in terms of the displacement field, this displacement function, if you like, which serves as the primary unknown thing that we're looking for. If we find the displacement field, then we know everything else. And that really sets up this issue of solving and posing boundary value problems. A boundary value problem really is nothing more than a statement of seeking a particular solution for this unknown displacement field, describing how a body deforms under applied loads, subject to these conditions that it has to satisfy all of these different equations, all 15 of those previous equations we showed, relating the strain and the displacement fields to one another, relating the strain and the stress fields to one another through the constitutive law, and lastly, satisfying the governing equations of equilibrium. But all of those could be represented just in terms of this unknown displacement field, with all of the other kind of quantities that we've assembled, along the way, being presumed known fields. In particular, if we're trying to characterize things like the rank 4 elasticity tensor, we presume to know what the stiffness of the material is. We can characterize that material behavior and its corresponding elastic constants by going and running some experiments and measuring some of these properties in a laboratory setting. Or similarly, we might know what distributed loads or body forces might be acting on this domain of interest, so we can prescribe what those external load conditions are. The thing that we don't know is the displacement field. And so when we set up these problems, really what we're setting up is a statement that says, here's the equation that I need to satisfy, or really the consolidated set of equations governing the elastic behavior that must be satisfied for deformation of some solid body. And what I want to know is how exactly does it deform under these prescribed loads and given these kind of prescribed material properties. Now, certainly that will depend on things like the geometry of this particular structure or solid object that we're looking at. But just stating that the solution that we're looking for satisfies this equation of equilibrium effectively is not sufficient to actually come up with a unique solution to boundary value problems in general. Typically, we need to, yes, say that we're searching for a solution that satisfies equilibrium and compatibility in the constitutive law, true, but we also need something else. And the something else are boundary conditions, which are effectively additional constraints that we have to impose. And usually they're imposed on the boundary of this particular structure or solid object that we're looking at. So to give you an example of what this might look like, suppose we had this continuum potato thing, which I'll call omega, and maybe on the boundary of this solid object, I might prescribe different boundary conditions. And these boundary conditions might come in two different flavors. There are displacement boundary conditions, such as the one shown in blue for gamma u, which will be the portion of the boundary over which I will choose to prescribe so-called displacement boundary conditions, or constraints imposed directly on the value of the displacement field along that particular boundary. The simplest one you can think of is just by insisting that the displacement at this constrained boundary, let's say that hatched region in blue, that the displacement field is fixed or constrained, such that it's just purely equal to zero. But it could be prescribed to be some non-zero value in general, which I'm denoting here with a u with an overbar, just to say that maybe I'm prescribing this u with an overbar over that particular portion of the domain, or on the boundary in particular. The other type of boundary condition that we can prescribe are traction boundary conditions, or in other words, external surface forces that we might apply. And we would apply those traction boundary conditions anywhere on the exterior surface where we're not directly prescribing the displacements. And there can be certainly traction boundary conditions that are describable kind of like an externally applied force or distributed load. And that could be represented in terms of prescribing directly the components of traction or the components of stress that are exposed on a particular surface. And the components of traction that are exposed on a particular surface will depend on the orientation of the exterior portion of the boundary. And we can relate those prescribed components of traction, which I'll call T with an overbar. We can relate those prescribed components of exterior surface traction to the corresponding components of stress through this kind of relation that involves the dot product between the particular surface normal n with the stress tensor itself. Now, that's not the only way that we can prescribe traction boundary conditions. And in fact, what you see in this figure is just as important as what you don't see. So even if I don't necessarily have a displacement boundary condition explicitly prescribed on this boundary as for gamma u, and even if I don't necessarily directly impose a particular load or distributed surface traction as I have kind of shown on the right here, it's possible that I could just have a free surface. But that still qualifies as just a particular case of a traction boundary condition for which that prescribed traction is simply the zero vector. So it's important to be specific in even including zero traction boundary conditions as nonetheless qualifying traction boundary conditions that we have to prescribe on the boundary. And as we'll see in a moment, in order to have a well-posed boundary value problem, we do need to prescribe either one of these two things, either displacements or traction everywhere on the boundary. A little bit more on that in a moment. But in general, I want to provide you with this formal definition of really what do I mean when I say a boundary value problem, it's nothing more than simply a statement of this problem which says I want to find a displacement field. And it might be helpful to consider this particular example statement that basically says find some displacement field, u, which is a continuous function necessarily, a priori I say that. Find this displacement field which satisfies some governing differential equation, such as the elasticity equations in this particular example, and which also satisfies some prescribed set of boundary conditions. And that can comprise displacement boundary conditions, direct constraints on the displacement field itself, or traction boundary conditions, which are somewhat indirect constraints on the value of the exposed components of stress on some portion of the boundary. Okay, so that's what a boundary value problem is. It's really nothing more than this particular statement. And the solution to boundary value problems ultimately furnishes not just the solution for this particular field U, but obviously all the other kind of fields that are derived from it. Strain, stress, internal force if we're looking at things in a one-dimensional context. But that's kind of the idea behind boundary conditions and boundary value problems more generally. All right. So what's a good example of a particular boundary value problem, and how do I actually define some of these boundary conditions? Suppose I had this block, as shown here, where it's just a two-dimensional problem to make things a little bit easier, and there's a different number of boundary conditions that I'm applying in different combinations. Along the bottom edge, I'm choosing to prescribe both components of displacement in the x direction and displacement in the y direction along that entire bottom surface. On the right surface, I'm prescribing directly the components of traction due to some possibly varying load or force per unit of area that I'm applying to that whole right edge. And maybe both of those components of traction, sigma xx and sigma xy, the normal and shear components of traction acting on that surface respectively, both of those might vary as a function of position, in this case with respect to the y coordinate. On the top face, it's a free surface. I'm not imposing any load there, but I still have to prescribe the components of traction that are exposed on that top face. Those being sigma yy, the normal component of stress exposed on that top face, and sigma xy, the shear component of traction exposed on that top face. Both of those being equal to 0. And then on the left face, kind of a curveball for you, but the idea is I could prescribe something of a combination of both displacement and traction so long as they don't necessarily conflict with one another. So in this particular example, I'm saying prescribe directly the x component of displacement by effectively preventing any kind of displacement in the x direction of this solid object on the left end of this block. That's kind of like I'm saying put this thing on rollers, where these rollers prevent separation, but allow possibly some sliding to occur. So the block could slide along these rollers, but it can't actually, create a gap or open up. And that condition is effectively equivalent to saying that I might constrain the normal displacement or the x component of displacement relative to that surface, but I'm disallowing there to be any kind of shear traction which could resist that sliding motion. So in order to prescribe that resulting shear traction acting over that surface is 0, or that it imposes no resistance, I have to insist that sigma xy, that component of shear traction, is equal to 0 on that surface. And this is a so-called well-posed boundary value problem. It has all the ingredients we really need to be able to uniquely solve for what the resulting displacement field would be for this block under these applied loads and with these prescribed kind of constraints or displacement boundary conditions at its various edges. Now, that's not true of all boundary value problems. Not all boundary value problems are created equal, unfortunately. Some are well posed and some are not well posed. And you might be baffled by this notion. What is well posed? It sounds very proper, doesn't it? But a mathematical statement of well-posedness really comprises three things. For a boundary value problem to be well-posed, it has to satisfy these conditions of existence, uniqueness, and stability. Existence is the requirement that a boundary value problem should have a solution. A solution for this problem should exist, in other words. And that might seem like an obvious statement, but sometimes there are problems which you might pose inadvertently which don't actually admit a solution at all. And we'll see exactly why or how that might come about. But just, for reference, it's possible that you might be over-constraining some problem to the point where it's just not even possible to come up with a solution for it. The next one, uniqueness, effectively says that even if there is a solution to a particular problem, even if I satisfy uniqueness, or rather if I satisfy existence of a solution, it's not necessarily the case that that solution will be unique. There might be more than one possible solution if the problem that I'm posing doesn't satisfy this uniqueness criterion. So uniqueness really insists that for a well-posed boundary value problem, not only should a solution exist, but that solution should be unique. And it basically means that there are no possible alternative solutions to choose from which satisfy all the equations and boundary conditions which you've prescribed. And we'll see where that can come into the picture. Usually, solution uniqueness becomes a problem when you have under constraints. You may not be imposing enough constraints to prevent, let's say, a structure from deforming or moving rigidly under whatever imposed loads you're putting on it. And then lastly, stability is one that's a little bit out of the context of what we'll be considering in today's lecture. We'll come back to this at a later time. But to give you an example of when might you have an issue with solution existence, suppose we had that same example, and instead of imposing on the left edge those boundary conditions where I said, let's constrain normal displacement along this left edge and, shear traction along this kind of left edge. Effectively, what I'm saying is I'm constraining displacement in this x direction. I'm constraining traction in the y direction. And as long as those two things are mutually orthogonal directions that I'm prescribing differing kind of components of displacement and traction in, then I have no conflict between, prescribing displacement this way has nothing to do with how I choose to prescribe either displacement or traction in the y direction. However, if I come back and I said, I would like to prescribe the x displacement along this edge in this direction, and wait, by the way, I also kind of want to prescribe what the resulting reaction force should be, or the sigma xx component of traction on this left face, because I expect it to be some particular value. I anticipate that that's what it should be based on, my intuition or some other argument that you might try to make. But the problem is, if you try to do both of those things, if you attempt to prescribe both displacement and traction at the same location along the boundary and in the same kind of component-wise direction, it just doesn't make any kind of sense. You can't prescribe what the reaction force should be at a support before you've actually gone about solving the problem and figuring out how things all work out. And you can kind of intuit that that's the case by considering the problem that we posed as maybe the second lecture when we went through solving a particular finite element problem. We had to solve this whole kind of system of equations for how the structure deformed before we could then come back and then solve for what the reaction force should be at the support. It just didn't make sense to prescribe what that reaction force should be before we kind of went through that whole process. So if you try to do this over constraint of prescribing both displacement and traction in the same direction at the same point along the boundary, you'll violate this condition of solution existence. So avoid doing that. Don't do that. In terms of solution uniqueness, this is another issue where, as I mentioned before, one way that you can have an issue with uniqueness is if you're not sufficiently constraining your problem of interest. And that could happen, as in this example, where I've removed the bottom support. And in this case, what would happen to this block if I have it sitting on rollers on this left edge and I have maybe some externally applied loads applied to the block along the right edge? If I'm not constraining it against moving vertically at all in the y direction, I don't have any rollers or any other additional constraints that prevents that rigid translation from happening. What'll happen is, well, this block will start to move. And certainly if you're solving a problem that admits dynamic behavior, and if you're solving transient structural dynamics problems, then there's no problem with doing this. But if we're solving problems, as in the case of quasi-statics, and as we're going to be considering the first portion of this class, then certainly this problem doesn't necessarily admit a unique solution. The block will stay in a state of equilibrium from these applied loads, but it might be translating, and we don't know exactly where it's going to be at some later time. So if you're not constraining a body against rigid motion, either preventing it from translating rigidly or rotating rigidly, then you can violate this condition of solution uniqueness. So you have to make sure that you're at least constraining it against rigid motion in order to have a unique solution. Okay, so in general, all of these different things that I've mentioned impose a few additional restrictions on how we actually go about defining boundary conditions in order to ensure that we have a well-posed boundary value problem. So the first one, in order to ensure solution existence, we have to make sure we're not over-constraining the problem. So make sure you don't define these conflicting constraints, like trying to prescribe a displacement and a traction at the same location along the boundary. Don't do that. And the other one, to ensure that we have a unique solution, we have to make sure that we are still sufficiently constraining this structure from deforming and preventing it from moving or translating rigidly. Now, the other thing to ensure that we have a unique solution is also we have to be specific about what the displacement and traction boundary conditions are along the entire region of the boundary of this solid object that we're looking at. If we're non-specific about what the particular traction or displacement is at some kind of missing portion of the boundary where we're saying, well, I don't know, is there a displacement boundary condition here, or is there a traction there? I don't know. Can we just leave it blank and just try to come up with a solution, and maybe that'll be good enough? Unfortunately, no. We have to be specific, and we have to say whether there is a traction here or whether there's a displacement boundary condition here. If you're not sure, if it looks like it's just a free surface, then you just prescribe zero traction there, and that's probably the easiest one to deal with. But it does mean that if you're trying to set up these problems in a mathematical context, then you really should give some attention to this and just make sure that you're prescribing displacements and tractions along the entire portion of the boundary when you're defining the problem that you're setting up. Otherwise, it's kind of ambiguous. You might not necessarily know what kind of problem you're getting out of it, and hence you'd violate this condition of solution uniqueness. All right, so that's all broadly speaking to give you a sense of what are these boundary value problems, how would we pose them in a two-dimensional sense or a three-dimensional sense. But the solution of boundary value problems in general is actually quite challenging. So challenging, in fact, that they had to come up with this whole special method called the finite element method to be able to solve such problems in general, particularly for 2D and 3D problems. Now, that doesn't mean that we can't solve these boundary value problems in an analytical sense using classical kind of mathematical tools. It just means that if you try to solve these more complicated problems in 2D and 3D, it requires a lot more mathematical background than I think we have time to go into in this class. Instead, I'll give you a flavor of how we solve these boundary value problems in a simple one-dimensional context. And to do this, let's revisit some of the previous developments of all of the governing equations of mechanics, but isolate attention to their one-dimensional analogs. So starting from the condition of the displacement field, or a function of position. In this case, just a simple one-dimensional function u representing axial displacement of some one-dimensional member, which might vary as a function of axial position x along the length of that member. So in other words, we have u as a function of x, which you could plot in a simple two-dimensional diagram. We insist that that function, or that kind of representation for the axial displacement field, is a continuous function in order to satisfy compatibility. We can, from that definition of displacement, define what is the resulting strained field, which is just the derivative of that displacement field. We can use our linear elastic constitutive law in one dimension. It's fairly simple. The axial stress in this one-dimensional member is simply proportional to the Young's modulus of the material multiplied by the strain in the material. The resultant force is just stress times cross-sectional area to give back the resultant cross-sectional force, and force equilibrium of any kind of finite slice of this member is determined as basically this simple governing differential equation, which we could derive, or which can just kind of recognize as being equivalent to the previously derived one-dimensional relationships expressed in terms of stress, but now just kind of multiplied by cross-sectional area. And this resulting force per unit of length, P, is what I'll call just a distributed load. So kind of think of it as a distributed axial load along the entire length of this member. We could put all those different equations together into one governing and differential equation to rule them all, expressed solely in terms of the unknown displacement field. And we can pose our boundary value problems in this one-dimensional sense, quite similarly to how we proceeded in the more general 2D and 3D cases. So again, boundary value problems in this case really amount to trying to solve for this a priori assumed continuous displacement field which satisfies this governing differential equation of elasticity in one dimensions, given known material properties, known cross-sectional properties of the member that we're looking at, known distributed loads or body forces that might act in an axial way along the length of this member, and in addition to having to satisfy these governing differential equations, satisfying equilibrium everywhere along the length, we also have to introduce boundary conditions in order to actually come up with existent and unique solutions to this particular problem. So I'll give you an example just to make things a little bit more concrete and to make things also tie back to some of the investigations we did early on in the class. We'll revisit this example of a simple one-dimensional member which has uniform cross-sectional area, uniform material properties, so the Young's modulus is constant, and it's subjected to this uniform distributed load, P, which has units of force per unit length. At the left end, we'll constrain it from displacing, or in other words, we impose a displacement boundary condition at this left end, and at the right end, the other boundary, where there's only really two boundaries in this one-dimensional object that we consider, the left boundary and the right boundary in a one-dimensional domain. At the right boundary, we choose to impose zero force there. But it doesn't necessarily mean that there isn't a boundary condition there. In fact, we are imposing a boundary condition. It is, in fact, however, a force boundary condition, kind of the one-dimensional analog of a traction boundary condition, imposing some constraint on what the applied load is on that right-hand end, just saying that it's equal to zero. All right, so we want to solve this boundary value problem now posed in one dimension, and the goal of this boundary value problem is to find what is the resulting solution for this axial displacement field, the function of position, which satisfies our governing differential equation of equilibrium in a pointwise sense everywhere along the member, and which additionally satisfies these two boundary conditions that we've imposed, a displacement boundary condition and a force boundary condition. Now, how do we actually solve boundary value problems? I called this lecture the solution of boundary value problems. And really, there are many ways that you could solve boundary value problems, but we'll start from maybe the simplest and most straightforward way of solving them by starting at the bottom, and then we'll work our way up. And by that I mean we start with this description of the resulting distributed load applied along the length of this member, which, if you like, you can actually interpret this distributed load as itself also being a function of position. So in that sense, the distributed load could be regarded as also a function or a field, and we could choose to plot what that function looks like in this diagram shown at the bottom right-hand corner of the screen. So if, let's say, this distributed load is constant, it's uniformly distributed over the entire length of this axial member, then we can plot that and show that it looks like some constant function that has uniform value all along the length. Now, given our steps of how we related different quantities to one another, the governing differential equation of force equilibrium gave us a differential relationship between this axial distributed load P and how the internal force F, also a function of position potentially along the entire length, how that derivative of the internal force field varied, that had to be equal to basically the relative applied distributed load. So as shown at the bottom, we have our statement of pointwise equilibrium in this axial member, shown as P equals minus the derivative of the force field with respect to x. Now, if we wanted to determine, given this applied external load, what is the resulting expression for the variation in the internal force throughout this entire member as a function of position, all we would need to do is take this expression, this differential equation, and integrate it, because it's just a one-dimensional governing differential equation. We can integrate that with respect to x rather straightforwardly. And all we have to do this is just take that existing function p, integrate it with respect to x, and introduce some extra constant of integration. I'll call that c. Now, we will come up then with some function f, which varies as a function of x, but the problem is we don't really know what this extra constant of integration is. In other words, we don't necessarily know or have a unique representation for this solution of the internal force within the member. Hence, you can see why having boundary conditions helps in solving and more specifically determining a unique solution for these particular solution fields of interest. We need boundary conditions, in other words, in order to specify some of these constants of integration that might come up once we try to integrate these differential relationships and solve for the ensuing solution fields. So in this case, we can actually take our force boundary condition, which says that the right-hand end of this member has to have zero internal force, effectively. That's kind of what that boundary condition tells us. And if we impose that boundary condition, then we can actually solve for this extra constant of integration c in order to figure out how that internal force varies. And noting that, in fact, this differential relationship integrates some constant function, what we expect to get out of this integration operation to determine how the internal force varies as a function of position is that we should expect to see that the internal force varies linearly along the length of this member. All right, well, that makes things fairly easy. We can use our boundary conditions to make that statement of how the internal force varies explicit and unique. We can also, given internal force, figure out what's the internal stress just by dividing by the cross-sectional area, assuming that the stress over the cross-section acts uniformly. And we can also divide the resulting internal stress along the length by the Young's modulus, inverting our constitutive relationship to determine what's the internal state of strain in this member at any point along the length. And then finally, we can come up with an expression that says what is the resulting displacement field, the thing that we wanted all along. What is the resulting solution for this actually varying displacement field, given now that we know how the internal strain varies throughout this axial member? And if we know a differential relationship between strain and displacement, where in fact strain is just the derivative of the displacement field, then all we need to do to recover the displacement field is integrate the strain field with respect to x, and again, we have to introduce some constant of integration, which I'll call d. But, as I said before, we can uniquely solve for that constant of integration by enforcing our other boundary condition, the one that says that the displacement at the left end of this member has to be equal to 0. And using that, we can integrate the linear function that we had previously for the force, divided by E times A to get strain. Integrate that linear function, we get some quadratically varying function. And we get this function, again, by integrating these different differential relationships, twice in this case, noting that effectively this resulting differential equation, the one that represents equilibrium as a second-order partial differential equation with respect to the displacement field. In order to recover the displacement field, we have to integrate that kind of resulting equation twice. Hence, the two-step procedure working backwards from distributed load to internal force to strain, and then finally to how the displacement varies along the length. And we could only do this because we had a well-posed boundary value problem. We had the right boundary conditions prescribed for this problem. But that's not always true. We may have situations where maybe we just goof up and we chose the wrong set of boundary value problems or rather the wrong set of prescribed boundary conditions, such that we just don't get a unique or existent solution. As in this case, where I might choose to, as I said before, be a little bit obtuse and insist that I'm going to prescribe what the reaction force is at this support, in addition to saying what the displacement is at this support. That's just not possible. It doesn't make any kind of physical sense. And certainly the way that I prescribe this boundary condition, insisting that the internal force or the reaction force at the left-hand end of this member be equal to 0, completely violates the assumptions of basically equilibrium. All right, so if I'm over-constraining these problems, effectively introducing, let's say, 3 constraints in this problem, where really there should only be 2 constraints, sufficient to solve for the 2 unknown constants of integration, then effectively I have 3 constraints, 2 unknowns. I have more equations than I have unknowns, and I effectively make it impossible for me to satisfy all 3 of these equations or constraints, given only these 2 unknown constants that I can, play around with. So that's another way of looking at this issue of solution existence, is that you have a mismatch between the number of constraint equations that you're imposing through these boundary conditions versus the number of unknowns that you might have to actually try to enforce those constraints. Solution uniqueness. Now this one might be a little bit tempting to say, well, if I didn't like the way that I was defining things previously, as maybe in this case, maybe I wanted to actually go about doing things a little bit differently and say, let's impose, let's just get rid of that displacement boundary condition. And if I already kind of know what the reaction force should be there, let's just put the reaction force there. And shouldn't that satisfy equilibrium? And, I have 2 equations now, 2 constraints that I'm imposing via boundary conditions. Should this not remain in a state of equilibrium? And should I not obtain a unique solution for this problem? Unfortunately, it turns out that if I choose to prescribe only force boundary conditions at both ends of this member, I will have 2 constraints, but it so happens that they'll be redundant. They tell me more or less the same information, and there's nothing that really helps me solve for that second constant of integration, d, in order to make the solution for the displacement field unique. So in essence, if I'm not constraining this problem against rigid motion by prescribing only force boundary conditions and not at least one displacement boundary condition to prevent the whole thing from possibly floating off, then I fail to satisfy solution uniqueness, and thus I don't have a unique solution for this problem. All right, where I'll end it is providing you with kind of a little bit of a fun game to make you think about, well, how do I exactly satisfy these conditions of solution existence and uniqueness? particularly focusing on this one-dimensional type of boundary value problem setup. So here I've given you just a collection of different examples to consider of one-dimensional boundary value problems that have different combinations of constraints imposed at different ends of this one-dimensional domain. So I want you to maybe take a moment. If you like, you can pause the video at this point and maybe ponder what you think each of these different boundary value problems, whether or not they satisfy the conditions of solution existence and uniqueness, and whether they should give you a resulting well-posed boundary value problem. When you're ready, you can hit the play button and I'll give you the answers now. All right, so hopefully you guessed correctly. If not, better luck next time, but you can certainly rationalize why some of these different constraints result in well-posed boundary value problems. The one that might have given you a little bit of trouble was probably the first one, actually, where both ends of this member were constrained against displacement. You might think, isn't this over-constraining the member? Am I not, imposing too many constraints? Well, there's nothing to say that I can't prescribe what the displacement is, even everywhere along the length. Certainly that makes solving these boundary value problems much easier, because I'm basically telling you what the solution is. The only issue that you have is when you have both a displacement boundary condition and a force boundary condition applied at the same location, which is certainly true for the bottom example or the one that's kind of at the top right here. There's also the issue of, again, like we had in that last example, having two forces but no constraints on displacement. That doesn't give me a unique solution. The bottom right is the trivial one that we started with, and the first example, which hopefully you can kind of have some confidence was correct. And the one at the bottom left basically neglected to say anything about what the boundary condition was at the right end of this member. You could say it's implied that there's no force there, but you really should be specific in saying whether or not there is a force there and specifically what that force is. If you think there's a zero force there, then you should say that there's a zero force there. All right, so that's all we have time for today. Obviously, I can't answer your questions immediately, but if you leave them in the chat or have other things or you want to reach out to me and discuss, you're more than welcome to do so. Otherwise, thank you for your attention, and I'll see you next time.